we start with Sanjay's second talk about symmetries in quantum dynamics.
Right. So yeah, I think we can continue from where we left off yesterday. So yesterday, just to give a recap, so there were these phenomena of weak ergodicity breaking, where we saw that Hamiltonians could either seem to be more block diagonal than expected. So you had, in the case of Hilbert space fragmentation, so the number of blocks grew exponentially with system size. This is also what Diptiman talked about. And then in the case of quantum many-body scars, we saw that there seemed to be one big block and one small block, and there are some anomalous eigenstates that belong to this block. And then the question was, how do you, so regular kind of the standard symmetries that we consider don't seem to capture this kind of a block diagonal structure. And the question was, how do you, what's the appropriate way to define symmetries so that this is captured? So you can't make this, so symmetries are operators that commute with the Hamiltonian, but you can't allow them to be completely non-local because this kind of trivializes the problem because you can write down eigenstate projectors. On the other hand, we saw that if you define symmetries in terms of families of Hamiltonians, so something like this, it seemed to be a more general definition. So this should hold for all jj, which is equivalent to hj j plus 1 commuting with q equal to 0 for all j. So basically I solve for all, so I'm given some set of terms that I'm interested in, and I solve for all operators that commute with each of these terms. Okay. Maybe I'll describe the general structure first and then go on to examples. I also gave a few examples yesterday. So the general structure is now any operator Q that satisfies this condition. So suppose I define the set C as the set of all Q that commute with each term of the Hamiltonian. This forms an algebra. Which means that if I take Q1 and Q2 belonging to C, then any linear combination also belongs to C. And then also like products, so Q1, Q2 and Q2, Q1. So this is closed under addition and multiplication. And similarly, the set of H's, so the algebra generated by these H's, the terms of the Hamiltonian, you can think of the algebra generated by these H's, which is called as the bond algebra. Right. This is basically everything that is obtained by, say, products of these H's, maybe at various sites, and linear combinations of them. And anything in C commutes with anything in A. So if I look at the space of all operators on the Hilbert space, so let's say this is the space of all operators on the Hilbert space. You have this algebra A, which is the set of all terms of my Hamiltonian. So that these are, you can think of these as algebra of symmetric terms. And there is an algebra that commutes with this, which is the commutant. So C is usually, we call it as the commutant algebra, which is the commutant of A. It's the commutant of the bond algebra. And C is the algebra of symmetries. So this is the symmetry algebra. Okay. So just a few nice properties of these algebras is that, so I usually start with Hermitian terms. Okay, so which means that this algebra A is closed under the conjugate transpose, like the dagger Hermitian conjugate. And which also means that you can see that if this is true, then C is also closed under Hermitian conjugation. Okay. So if some Q belongs to C, so I can also add this property here. This is means that Q dagger also belongs to C. And this is a property that follows because we are looking at Hermitian terms and then commutants of Hermitian terms. Okay. And so these are you can either just so there is a name for such associative algebras. So these are associative algebras, not to be confused with Lie algebras. So these kinds of matrix algebras which satisfy this condition, they are sometimes referred to as dagger algebras, or more fancily sometimes von Neumann algebras. Also, yeah, you need a small technical condition that identity belongs to this algebra, but that I think you can trivially just put in by hand. And if some of you are familiar with von Neumann algebras, like there are many types of these, and this is type 1, but you can ignore all of these. Like these are just, I'm working with a finite dimensional Hilbert space, so these are just matrices and algebras of matrices. There are infinite dimensional versions which are much more exotic, which I will not consider. Oh yeah, so this is the, suppose, I mean, this is just a sketch. Like, so suppose I have the space of all operators on my Hilbert space, then I can, A is some algebra generated by the terms of my Hamiltonian. So this is the set of all symmetric terms. And the commutant of this, like I look at all operators that commute with this algebra, that is what is the commutant algebra or the algebra of symmetry operators. And I'll give you examples which should make this more clear. Yeah. So yeah, that's a good point. Yeah. So so usually, so maybe I'll get to that. Yeah. So yeah, so there are this condition. These are called dagger algebras, and there is a nice theorem on these kinds of algebras which says that the commutant of the commutant is the algebra itself. So this is called the double commutant theorem, which means that the set of all operators, so if I just compute what is, so H, which commutes with the entire algebra C. So suppose I define H as the operators that commute with this entire algebra C. This is just the algebra A. Which means that if I just look at the set of all operators that commute with the symmetry, that is precisely this algebra A. So this C is the centralizer of A and vice versa. And this is, I mean, this is again proven more generally for von Neumann algebras, even in the infinite dimensional case, but I'll just need a baby version of that, which is in the finite dimensional case. Okay, so what that means is that any operator that is symmetric under this symmetries in C lies in this algebra A, which means that you can express any symmetric operator in terms of these local terms that I started out with. Right? So this is really the exhaustive algebra of symmetric terms. And which also means that any symmetric term is some function of like function defined in the loose sense of these local bond terms. Right? And this, yeah. Yeah. Right. Yeah. Yeah. So yeah, the algorithm of splitting is not clear. So, but if I'm given a set of terms, I can, for that set of terms, I can define an algebra and then compute the commutant of that. What usually happens is that the precise way you split things doesn't matter because you generate, ultimately, if you take products of those terms and linear combinations, you end up with the same algebra. Right. So for example, I don't know. So if I have an algebra generated by XX and Z, right? This is the same algebra as I don't know. So for example, I'm struggling to think of a simple example, but so maybe let me just put this in this way. So it turns out that this is the same algebra as this. Yeah. 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 So all of this is like in yesterday's talk, I described the physics of why we are studying these algebras, and those are like these weaker godicity breaking and so on. Yeah. Okay. Yeah. I can give you. Yeah, you can do that, but here I have a physical restriction. So all of the physics is coming in from the fact that this is generated by local terms. So if I just choose a random algebra here, there is no locally generated bond algebra. So somehow I want my symmetries to be symmetries of some family of local Hamiltonians. Otherwise, yeah, physically it's not well motivated, and I'll maybe give some examples of where there is no local algebra. Yeah. Yeah. You can, I mean, so the algebra, so yeah, so maybe let's do that example. So suppose I have two algebras, like which is one is XX plus YY, right? And the other algebra is like XX and YY. So by this, I just mean I take all terms. So the commutants of these are different, right? So the commutant of this will have some U1 symmetry, right? So there is all powers of this U1 symmetry and probably also some kind of a discrete Z2 symmetry, right? Whereas this will not have a U1 symmetry. So this will just have these discrete symmetries, right? So the commutant really depends on what family of Hamiltonians I'm looking at. Here, the appropriate families are the families of, say, XX models, whereas here it would be XY models, right? So yeah, the answer depends, but in many cases, like I showed here, if I take the XX and Z terms separately, it just turns out that maybe I should also include a J plus 1 here, but it turns out that if I group them like this, you get the same algebra. Like so, and the way you can show that is you can compute the commutant of this, the commutant of this, and if the commutants are equal, the algebras are also equal by this double commutant theorem. So these are like uniquely associated with each other. Okay. Right. Yeah. So I should maybe I should give some references for all of this. So this way of thinking about symmetries in terms of like families of Hamiltonians, it is quite standard in the quantum information literature. So there are papers dating back to Zanardi in 2001, and then lots of papers later, where this is how they somehow think of symmetries, but somehow that's not standard in our field of physics. The paper which we were very inspired by was a paper by Reed and Salure in 2007, where they apply this way of thinking about symmetries in terms of these bond algebras to some exotic cases, which I will maybe discuss later. And then we applied it to much larger set of symmetries in 2021 to 2023. Okay, so any questions so far? Or Otherwise, I'll just give some examples. Okay, before examples, I think I should also mention the important part. So, okay, what's the point of having this pair of algebras? So there is another important result, which is known as sometimes called the Wedderburn decomposition, or sometimes also the Artin-Wedderburn decomposition, which says that whenever you have a matrix or a von Neumann algebra of, or whenever you have a pair of these algebras, which are commutants of each other, you can always decompose operators in this manner. So I'll write out the expression first and then explain it. So yeah. No, right. So these are just abstract mathematical objects. Right. So this is what this is saying is that if I take any operator in A, there is some unitary transformation, which is this W and W dagger, where I can bring it to a block diagonal form. And you see that this might resemble symmetry sector. So if I take, say, some operator, so choose maybe this algebra, there is always a unitary transformation to a block diagonal form, where this block diagonal form is nothing but something that looks like this. So M is any matrix, which depends on the operator that you're choosing, identity matrix. And these capital D lambdas and small d lambdas are the dimensions of the irreducible representations. So irreps of A and irreps of C. I'll give you a concrete example in a bit. And the point is that, okay, so certainly you can bring A to this form, but the same unitary transformation takes C to this form, where identity is on the first copy and an arbitrary matrix is on the second copy. So you see that these two will always commute with each other, right? So that this is just a basis transformation. Whenever you have this kind of a commuting set of algebras, you can do this basis transformation, and that is a special case of what is known as the Wedderburn theorem. Okay, so if I look at this kind of a block decomposition, there are some big blocks which are labeled by lambda. So let's say there is some lambda 1, lambda 2, and lambda 3, and so on. And there are within each big block, this matrix has the form M tensor identity, which means that the same matrix is being repeated some number of times. So this is being repeated, say d lambda 1 number of times, and then maybe I should use a different color. So within each of these lambda 2, there is some other matrix which is being repeated like d lambda 2 number of times, and so on. Right? So there is similar things here. So HA is basically the set of symmetric operators, and this is giving a way to sort of block diagonalize your symmetry operators. So in the case where C forms a group, you know all of this, like these are just quantum numbers of your symmetry, but this is more a way of doing this starting from this bond algebra. Okay, so just to give a concrete example, in the case of SU2 symmetry, these so I should also say that these blocks are themselves have dimensions capital D lambda 1, and this has dimension capital D lambda 2, and so on. Okay. So in the case of SU2 symmetries, you can write this bond algebra as Sj dot Sj plus 1. And the commutant is basically the SU2 symmetry, which is just Sx total, Sy total, and Sz total. Right, so any power of these would commute with these S-dot S terms. And what this is saying is that you can always bring any SU2 symmetric operator into this form. So it turns out that if you work this out, these lambdas are basically the S square eigenvalues. So these are different S square eigenvalues that you get from here. The small d lambdas are the degeneracies, so which are, so say S square is lambda times lambda plus 1. The small d lambdas are, I think, 2 lambda plus 1. Like just the degeneracies that you get in these SU2 symmetric systems. Like for a given S square eigenvalues, the SZ can take many values. So you get the degeneracy because you're repeating the matrix. And then there is some expression for capital D lambda, which I don't remember off the top of my head, but these are the sizes of these symmetry sectors. Okay. And in this case, it turns out that this bond algebra is basically the group algebra of the symmetric group on L sites. So which is just the set of permutations. So it's if you look at if you stare at the S dot S operators, you will see that this S dot S operator is basically the permutation operator between sites J and J plus 1. So this is just the group algebra of the permutation group. And this is just the enveloping algebra of SU2, or like, yeah, or you can just very loosely think of it as the SU2 algebra, right? And this correspondence between the permutation group and SU2 group, you might have heard of this as the Schur-Weil duality. I mean, if you're not familiar with this, it's fine, but this is just a special case of this more general result. Okay. Yeah, that's right. Yeah, so there is some, yeah, so in simpler cases, like if you have an abelian symmetry, so if C is abelian, then what you can show is that all of these small d lambdas are 1, because these small d lambdas are the irreducible representations of C, and if C is abelian, there are only one-dimensional irreps. Right? Yeah. Yeah, I mean, there is still a duality. In the sense that like these two are interchangeable, right? So there is some decomposition of this form. Yeah, it's a trivial kind of a duality, but yeah, there is still a. Now you can ask how many operators there are in the commutant, right? So you want to, so yeah, so maybe I should get back to the motivation. So really what we were interested in the case of fragmentation was to understand the sizes of these blocks and say count the total number of blocks. If you just look at the total number of blocks, so the number of blocks scales as is just in this mathematical notation. It's just the sum over lambda small d lambda, which you can show that it scales in the same way as with system size as sum over lambda d lambda square. So there are bounds you can do. And this quantity here is the dimension of the commutant, which means if I just look at how many operators there are of this form, number of linearly independent operators is just sum over lambda d lambda square. And this is basically the dimension of the commutant, right? So, and my claim is that these two scale in the same way. So if say this is exponential in system size, then this is exponential, and then vice versa. You can show this more carefully. Okay. So so let me just give you some more examples. If so, I think yesterday I showed examples of Z2 symmetry where your bond algebra was XX. And Z, the commutant was basically generated by product of Z, and the dimension of the commutant here was just 2 because this is just identity and product of Z. So there are just 2 linearly independent operators here. And that is how you find 2 blocks for a Z2 symmetry. Okay. And then you can also do this for a U1 symmetry, which I also mentioned yesterday. So you take XX and Z. The commutant is basically generated by sum over Zj, which if you look at how many operators, linearly independent operators there are, this is just identity, sum over Z, the whole square, and so on, up to sum over Z to the power L plus 1, or no, sum over Z to the L. And so so the dimension of the commutant is L plus 1, which is basically the number of blocks you get with a U1 symmetry. So your spin can take values from minus L over 2 to L over 2, and you count them. It's basically the dimension of the commutant. Okay. Right. So another way of sort of interpreting these symmetry sectors is to just think of these. So I said that you can. The whole point of this is to sort of understand symmetries and symmetry sectors without any explicit reference to the symmetry itself. So I'm completely working in terms of these local terms that generate my bond algebra, and then I'm sort of doing this kind of a computation. One way of thinking about this block decomposition is to just ask, what is the basis in which all of my bond terms are simultaneously block diagonal? So you ask, what is the basis in which, so these bond terms, as you can see in all of these examples, the neighboring bond terms do not commute with each other, right? So you cannot diagonalize them simultaneously, but you can ask, is there a simultaneous block diagonal form I can bring them into? And it turns out that the answer to this is exactly this kind of a representation theory. So if I just take my different terms and try to block diagonalize them simultaneously, I will end up with this answer. Like this is the unitary that simultaneously block diagonalizes my set of matrices. And this, it turns out, is a sort of a numerical procedure. If I want to do this on a computer and try to find these symmetry sectors, I can just work with these terms here, and there are well-known algorithms for this simultaneous block diagonalization of matrices, which you can use to find these symmetry sectors. Okay. So and in this way of doing things, I have no reference to quantum numbers or quantum numbers of my symmetry or group labels or anything like that. I'm just working with my Hamiltonian terms and then trying to block diagonalize them simultaneously. Okay. Right. And now you can imagine that, so in this way of doing things, you can end up with symmetries that are much more general than your conventional set of symmetries. There is no reason that objects in C should form a group or some nice, that there is no reason that there should be any nice structure. And in fact, that is what we find, which I will illustrate with an example of fragmentation. Is this clear so far? Okay, so let's consider this model which was introduced in this paper by Sala, and I think Tibor is the first author. Tibor, Frank Pullman in 2020. I think this model was studied, but in the context of fragmentation, this is the work that introduced this, and this is known as the TJZ model. So this is a model of free fermions, or not necessarily fermions, but then you consider, say, free particles which are labeled by some up or down spin. And then you can consider a model where these up spins can hop freely, or the down spins can hop freely. Right? But what is not allowed is that the up spins and down spins, they're not allowed to cross. Right? So you can consider a set of terms. I can explicitly write down hopping terms that do this. Right? And then you can try to go through this exercise with this set of terms. But now, before the mathematical part, let's see what the symmetries of this problem are. So if I were very naive and I did not look very carefully, I would say that there are two U1 symmetries. So the total number of up spins is conserved because up can hop. The total number of down spins is conserved. Right? There are two U1 symmetries. Beyond that, it's hard to identify any kind of obvious like symmetries, obvious in the sense that it's not a sum of local terms. Right? But if you look more carefully, there are these additional pattern conservations or irreducible strings like what Deeptiman was showing yesterday. So for example, if I start with a configuration with up and down spins here, this down spin can never go to the left of this up spin. So there is this global pattern of up and down spins which is conserved. And similarly, if I start with some configuration that looks like this with say zeros in between, this pattern of up and down spins is conserved, right? So you can treat that as the irreducible string. And so the question is, how do you write down conservation laws that correspond to this pattern? But my claim is that if you go through this procedure blindly, you will discover such laws. And in fact, like if you do this, it's not very hard to do. So you find that locally there are, so if I just write these terms, let me just say there are some hopping terms corresponding to these rules. You can look at, so it turns out that you can write down these kinds of a conservation equations, H, J plus 1. And this is true locally, and this is also true locally. So J plus N sigma J plus 1, H, J plus 1. So if I just look at each term, these are the operators that commute. So you can ask what are the operators. Now I want to find global operators that commute with each local term. Yeah. Yeah, so the strategy is to sort of, I have my HJJ plus 1, and I want to ask, so suppose there is some global operator that commutes with this, I'm just asking what the pieces of this operator can be. And any operator that is composed of these two pieces will commute with these local terms, right? And it's easy to come up with operators that are composed with pieces. Obviously, the total spin is just composed of this piece, right? But you can also utilize the fact that there is this other piece being conserved. If you, for example, look at operators that look like sigma 1, sigma 2. So here sigmas are the spins, I should say. J1, J2. So if you consider an operator of this form, so you consider how does this look when this operator sits on sites J and J plus 1. There is one piece which will look like this, and there is another piece that will look like this, right? And this is a conserved quantity which is completely independent of this of these two. So there is no way to go from here to here. It's not the square or product of these. If I take, especially if I take these to be up and down spins. Okay, so this is like a completely new conservation law which you can discover by just solving for operators that commute with each term separately. Okay, and it turns out there is an infinite series of conservation laws. So you can have n sigma 1, sigma 2, J2, sigma k, jk for any pattern of spins with the constraint that J1 is less than J2 is less than jk. Right? In total, you find that the number of conservation laws, which is the dimension of the commutant, is just basically spanned by operators of this form, and which you can count to be, I think it is 2 to the L plus 1 minus 1. But the point is that this grows exponentially with system size. And I said that the number of blocks is basically proportional to the dimension of the commutant, which is exponentially large. And so this is a fragmented model. So whenever you find that the dimension of the commutant is exponentially large, that is what we call as fragmentation. Yeah. Right. Yeah, so that is a very good and also deep question. So yeah, so integrable models are different. So here, what I'm saying is that this commutant is associated with a family of Hamiltonians. Whereas if you take the infinite series of conservation laws in, say, the XXZ model, it turns out there is no family of Hamiltonians. There is almost a unique association. So if I give you the conservation law, I can tell you the XXZ Hamiltonian uniquely. So it doesn't really fit into this framework. Right? So these are really conservation laws which are associated with some larger family. Sorry? Yeah, so there is this simultaneous block diagonalization. So you can, and I'll also maybe get to more algorithms, but one way of doing this is you just write down this block diagonalization, and once you have these blocks, you can write down operators in C and look for local ones or whatever you want. Okay. Right, so this is an example of fragmentation where things were kind of easy to understand. We already knew, yeah. In these models, you mean? No, I will get to examples of how to incorporate translation invariance into this kind of, it turns out even there is a family. So there is no unique association. Yeah. But just family is defined in a slightly different way. But I'll hopefully get to some examples. Right. Yeah. So this kind of fragmentation was sort of easy to see. You can say, okay, why did you need all of these algorithms to do this? You can already see that the pattern is conserved, but there are more non-trivial examples of fragmentation, and this is where the paper by Reed and Salyer is very nice. So they actually discussed this already back in 2007 when fragmentation was not yet, the term was not yet coined. So they were looking at models which are spin one models of this sort, Sj dot Sj plus 1, the whole square. These are spin one Hamiltonians. And what they found was that, I forget the sign, whether it was positive or negative, but what they found that was for a system size of 10, the number of ground states was something like 10,000. Right, so which is very weird. Why do you have such a large ground state space for this model? And this is, and then what they showed was that actually so the way you can understand these ground states is due to extra symmetries in this system. And the way you define these symmetries are exactly through this kind of a bond algebra and commutant framework. So it turns out if you define the bond algebra this way, S dot S whole square, this forms something known as the temporally Lieb algebra. And you can, like the representations of these temporally Lieb algebras are all kind of well established. So all of these numbers, capital D lambda and small d lambdas are known. And you can also write down the commutant, which is roughly speaking like of a similar form. So you have these strings of non-local operators, which I think in their they have different labels, but just to give you an idea, so you have some alpha 1, beta 1, alpha 2, beta 2, and so on, and then a sum which is like J1 less than J2 less than Jk. So you can actually maybe I should J2, J3, and then up to Jk. Yeah, so something of this sort. Right. So you have these exponentially many non-local operators which commute with this Hamiltonian, and there is also nice relations with the commutant of the temporally leap algebra. All right. So this this kind of a fragmentation is not very easy to see just as some patterns unless you write it in a very nice basis. And this fragmentation is what we called as quantum fragmentation, because it's hard to see this in a classical basis. So, and this is all classical stuff. And you can make this kind of a distinction even for regular symmetries, like a total spin conservation is just a classical symmetry. So your product states can be, so the basis that block diagonalizes my Hamiltonian is the product state basis, whereas if your basis is more complicated, those are like somehow intrinsically quantum. Yeah, so these are some raising operators. Now I don't remember the exact form. So these are something like S plus square or something like that, or some S plus. And there are some strings of these S plus square and S minus square, which commute with each of these terms. Okay, so since I'm again running short on time, I'll just quickly go over quantum many-body scars, and it turns out that again the algorithm is similar. So you find if you define bond algebras appropriately, so there is some local set of terms. What you find is that, so if you remember, quantum many-body scars were basically these eigenstates which are special and solvable. They are nice looking. It turns out that the commutant is essentially projectors onto these special eigenstates. So if these are, say, psi n, psi 1, so let's say psi 1, psi 2, psi 3, and so on up to psi n. So you can get the projectors onto these states as the commutant. Right? And projectors onto these states, you can, if you do this block diagonalization for this algebra, this is easy to do by hand. You get that there is this one whole block, and then there are these small blocks which are essentially just the eigenstates themselves. So you have psi 1, psi 2, and so on. Right. And so this also sort of gives a definition for what exactly you mean by a quantum many-body scar. Yeah. Yeah. Yeah, it's the same thing. So I can write down an explicit expression for this, which in the case of scars, which I showed yesterday, which were these SU2 multiplets. Yeah, you don't know. I mean, but if given a bond algebra, you can find the scars. Like given a family of Hamiltonians that have this state of eigenstates, you can find the scars. That is. Yeah. Right. So this is not a recipe for finding scars in a particular Hamiltonian. Like you can do the search for a family of Hamiltonians, and if you find that the commutant is of this form, you know that there are scars. Yeah. I mean, what we know is that for all of the family, for all of the scars that are in the literature, at least these exact scars, there is an associated local bond algebra, which is like generated by local terms, such that the commutant is of this form. Right? So for the particular family which I described yesterday, there is some particular set of terms which are something like, you can think of, like you have the Heisenberg terms, and then you have some total SZ and some other terms. But so this is what is the case for the family of scars which I discussed yesterday. PXP is a different story because the block diagonalization itself is approximate. So we don't know how to deal with such cases. But in cases where there are exact scars, my point is just that they can be treated as symmetries in the sense that you have a bond algebra, which is generated by local terms, and you find the commutant, you will find the scars. Right? Okay. Onto the scars. Yeah. And it turns out like if you in some sense, like frustration-free systems that Haruki talked about are scars in this sense, right? So if you have a frustration-free system where you have sums of where you have a Hamiltonian such that you simultaneously minimize the energy of some state with each of these terms. Now, if I look at a bond algebra generated by these terms, I will find that the projector onto this ground state, this frustration-free ground state, is in the commutant. So yeah. Yeah. No, so this is not all eigenstates. So that's the difference, and I'm getting to that. So earlier I said that, okay, eigenstate projectors are kind of trivial, so we should throw them out. The difference between scars and regular eigenstates is this fact that really scars are states which are associated with families of Hamiltonians. So it's very rare for a state. So suppose I have a state, and then suppose I demand that there is an entire family of Hamiltonians that have the same state as an eigenstate, right? So typically for eigenstates of Hamiltonians, so if I just take an eigenstate at random, and I ask what are the local Hamiltonians that have this state as an eigenstate, the answer is that just the original Hamiltonian, that's the unique Hamiltonian that has this as an eigenstate. Right? So there is a one-to-one association between local Hamiltonians and eigenstates, and that one-to-one association breaks down for quantum scars. Right? So because of this structure, like so there is an entire family that I can write down which has this scar as an eigenstate. Right? So there is no, in other words, there is no information of the Hamiltonian in the eigenstate. So there is in general eigenstates, like if you do a numerical exercise, you just take an eigenstate, try to construct a local Hamiltonian, you'll find that there is only one local Hamiltonian, right, that has this as an eigenstate. And this sort of turns out this is also related to the eigenstate thermalization hypothesis, which I was describing yesterday. So this ETH is what it says is that, so if you take eigenstates of Hamiltonians, the reduced density matrix sort of looks like e to the minus beta h, right? This is the definition of these thermal states. And so what this means is that if I just look at a single eigenstate, the information of the Hamiltonian should be there in this eigenstate, right? Because the reduced density matrices look like e to the minus beta h. And so that means that at least in principle, you should be able to reconstruct your Hamiltonian from the eigenstate. And that is not possible for quantum scars. Okay. So this sort of also gives you a definition of what quantum scars are. So they're really these simultaneous eigenstates. And then for these, so maybe I'll not get into details of these, but for another, so I said that this algebra A is like the exhaustive algebra of symmetric operators. And you can actually exploit this in the case of quantum scars to write down, so given a set of quantum scars, what are the exhaustive set of Hamiltonians that have these quantum scars, and there are some nice restrictions that come up there. So for example, if you have this set of quantum scars which I described yesterday, it turns out all local Hamiltonians should have them as equally spaced eigenstates, so there is no way of tuning the spacing between them while maintaining locality. And you can show such statements using this kind of a exhaustive correspondence. Okay, so maybe let's return to something that maybe which is a bit more familiar. So which is to connect all of this to things which have been mentioned earlier in this conference. So if I suppose I want to do this procedure for G symmetric operators. So how do I do this? Suppose, yeah. Yeah, so I think so earlier, at least when these quantum scars were first discovered, there is something called classical scars. Like I mean, so there are something like which are called scars in the sense that, like, if I take ball bouncing around in some kind of a boundary with some boundary conditions, it turns out that there can be these rare periodic orbits which, when you quantize the problem, look like anomalous eigenstates, and somehow that was the analogy. But for the many body case, I think there is like such an analogy sort of breaks down. So it's not very clear what the, it's and we are just kind of stuck with the terminology. Okay, so suppose you do this, want to do this for like G symmetric operators, so you can write down a Hilbert space which is just composed of group degrees of freedom, which I think you have seen earlier in this conference. So, and you can also define operators which are like the left multiplication and right multiplication. H times G. And you can also define operators which sort of look at the representation. So these are just local operators that I can define on this Hilbert space, which do various things to my state space. Right? And you can show that the bond algebra for, if I want my symmetry operators to be G symmetric, so suppose my symmetry operator, so if I want the commutant to be product of RG, G, so this forms a group, which is, so G is chosen from this group, capital G, right? So this forms a group. You can write down the bond algebra for this to be something like LG and trace of Z gamma, J plus 1, and there is a dagger here. So there is a set of local operators which I can write down such that if I solve for the commutant, I get basically the algebra of G symmetric operators. Yeah, I'll maybe have more things to say about this, but so here you can also do this for symmetries which are not just the group-like symmetries. So you can also do this for rep G, which I think was also discussed by Apurv and Frank. So if you take the bond algebra or the set of local operators which are defined as LG, RG, LG inverse, and this Z gamma of J, and you try to solve for the commutant, you find that there is actually, you find a matrix product operator, which is labeled by these Z gammas. And these are the matrix product operators that Frank was talking about. So here I should remind you that Z gamma here is really a matrix of operators in general, because gamma is the representation of this group. And if I have a non-abelian group, like in the case of say S3 or something, then these Z gammas are really like matrices. Okay. And what you find if you choose the right bond algebra, there is a commutant which really is the set of matrix product operators which are labeled by this gamma representation. Okay. And this kind of a commutant, so here this commutant had a group structure. But here it is no longer a group, it is this fusion category, which is the rep G category. Okay. And you can compute, so by this, I mean, just to be very concrete, there is some fusion rule. So if I take two operators of this form, their multiplication is really the sum of different representations. So I'll list. So if I take this as a shorthand notation, which was similar to what Frank was using. So if I take two of these MPOs, there is some way of truncating this. So you can write this as a sum of different MPOs, which are, so suppose this is Z gamma and this is Z gamma prime. This is some Z gamma double prime, which is summed over, which is basically the same relations as, suppose I have something like this. Right. So depending on the fusion rules, I can get these kinds of non-local or matrix product operators. So this sort of brings me to what is the precise connection between all of this and what was described earlier. And it turns out that, well, here I'm really specifying a particular Hilbert space. So given this bond algebra, I compute the commutant assuming some kind of a Hilbert space here. So, but what was done earlier in Frank and Apur's talks was really that there was, you can think of this much more abstractly. So instead of thinking about a particular Hilbert space and a particular representation, you just abstract one level and say that, okay, there are some objects in somewhere that form a category C, and then you can ask, can you, in cases where the C forms a fusion category, what can you say about the sort of the bond algebra or algebra of Hamiltonian terms that have this fusion category as a symmetry? And it turns out that whenever you have this kind of a fusion category, you can abstract out, just as going from like representations of the group to the group itself. Like there is one level of abstraction that you can do, such that this A also has some categorical structure. And this categorical structure is basically like the algebra of terms of your Hamiltonian, which appear here. Okay, so in cases where this is a fusion category, it turns out that this is also some kind of a category, and this is the bimodule category that Frank was talking about. Right? But then but there you think of this abstractly. So there is also a choice of Hilbert space, like the choice of module that you need to choose. But here I have done this just by fixing a particular module. And it's not clear that this kind of an abstraction can always be done. So in the cases where this is a fusion category, we know, and there is this huge body of literature on these non-invertible symmetries and fusion category symmetries. But if you fix a Hilbert space, we see that there are many more structures that can arise. Like as I've showed you, you can get fragmentation, you can also get continuous symmetries, you can get scars. And all of these don't form a fusion category, at least not in any obvious way. So I think so. So this is more general in the sense that, like, okay, we are sacrificing some generality by fixing the Hilbert space, but then we also get more general symmetries. But then if you allow for arbitrary Hilbert spaces, you can work with fusion categories and there is, I think, it would be interesting to sort of generalize all of this more abstractly, if it is at all possible. Yeah. Yeah, so it's not immediately clear, but you can, again, you can work out the local commutation rules like what I showed you, and you will find that it's just this product of MPO tensors. They appear naturally as some MPO tensors that commute with these. But yeah, it will involve some work, but it can be shown analytically. Is it the complete set? Yeah. So even that is possible to show in this simple cases. I mean, you just ask what are all the two-site operators that commute with this and this, and you can show that they are just these MPO. They can be spanned by these products of matrix product operators. Yeah. No, but this is like arbitrary coefficients, right? Like, so there is no. Yeah, it's an Ising model, but you mean if there is a free fermion mapping? Yeah, so I mean I cannot immediately rule that out, but yeah, I don't know in that sense. But here I should say that you can also take products of these terms. Whenever I write down bond algebras, I don't necessarily have linear superpositions in mind. You can also take like products of these. So if I take this term and then multiply it by this term, even in the Ising model, so suppose I have like xx and z, and then I just take xx times z, that is not free fermion. Here, I think there is nothing, like the full commutant is just the rep G symmetry. And yeah, it's a global symmetries, which happens to have a fusion category structure. And because of that, you can also work more abstractly and connect it to MPO symmetries. Yeah, I think it would thermalize. Yeah. Well, I think you can, it shouldn't be too hard to come up with examples like that. Like you just take one of the states which has rep G symmetry and try to make it a scar. So yeah, so scars are easy to kind of cook up. Yeah, so you can just take if the state is simple enough, it's almost always possible to. Okay. Right. So okay. So this was the connection, and then there are also more aspects which again maybe I'll just briefly mention, and then you can ask the experts on these kinds of things. So it turns out that this bond algebra of operators. So you have the algebra A. Say let's for concreteness take the Ising Z2 bond algebra. It turns out that you can, so there is this whole understanding of symmetric operators in terms of boundaries of topological orders. So suppose I have a 2D topological order. It turns out that you can associate these bond algebra terms to various lines, anion lines on the boundary of this topological order. And this is part of what is known as SymTFT, which I think Apurv mentioned, but we did not have a detailed talk on this. But basically, it turns out you can treat this E as being like this XX line. So usually this is done in the opposite way. So E is this ZZ line, and then this M is this XX line. And so you're thinking of your spin chain or your 1D system being at the boundary of a 2D topological order. And the algebra of these lines, these Wilson lines and 't lines, is basically the algebra of Z2 symmetric operators. So if this is, say, the Z2 topological order. Okay, and the fact that these anti-commute, so if I just take zj plus 1 and xj plus 1, these anti-commute, and this is related to the fact that E and M have they braid with non-trivially, or like with a phase height, with a -1 phase. And this is really was, I think, illustrated in papers by Arko and Xiaogang Wen, and also Apurv et al. Back in, I think, maybe 2022, and probably there are more papers that I don't know of. Okay. And again, so these bond algebras sort of naturally turn up in these discussions just by this kind of a correspondence, that there is the algebra of terms here are, at least when things are fusion categories and when C has some nice structure, the algebra of bond operators are the algebras of lines that end on the boundary. And you can, yeah. Yeah, I'll get to that. Yeah, so there is a way of getting Kramers 1 year, but yeah, so. Right, also I should say that, yeah, so there is this kind of an association. So now you can go in multiple directions here. So I should say that all of this only holds when C is a fusion category, which is not the most general case, but this is the case which has been discussed most here. So now you can do things like you can understand phases of matter using these bond algebras. So usually phases of matter are thought of as condensing one of these kinds of anyons on the boundary of topological order. So if you condense the E anion, which is like saying I'm only allowed a ZZ term in my Hamiltonian. So when you condense things, you're not allowed to put this term. That is like the ferromagnetic phase of the Ising model, or the ferromagnetic phase of Z2 symmetric systems. On the other hand, if I condense an M anion, I'm only allowed to put this other term here, and this is like the paramagnetic phase. Right? So there is a, again, just from these bond algebras and these correspondences, you can understand these phenomena. And dualities can also be sort of understood here, and this goes back to actually work by Zohar Nusinov and Ortiz. Back in 2011 or so. So the duality, as you might have heard in this conference, is basically just the switching of E and M, or the EM permutation in this topological order. So that is like basically switching these two lines. So since this has been identified with E and X, and this is the Kramers 1 year duality. At least, okay, this is the Kramers 1 year, roughly speaking, because there are things like half translations and which Pranay talked about. Okay, so yeah, so whenever this is a fusion category C, there is some algebra of boundary lines, and you can, in principle, do this, though I would not be able to do it because I don't know these things very well. Okay. So now, okay, how do you deal with things like half translations and translations? It turns out you can also incorporate these by defining families appropriately. So what do I mean by a family? So let's just take a simple example where I want the commutant to be the translation symmetry. Right? So obviously, yeah. Yeah, so I mean, I don't understand this well enough to really construct that, but I think there you have to get rid of the tensor product structure of the Hilbert space, and I'm sure it's possible to write down a bond algebra, but yeah, you'd have to ask Apurva or so. Right, so suppose I want to understand things like translations or like these half translations in this language. So I want the commutant to be things like T. So obviously anything in the bond algebra should commute with the translations. And it turns out you can choose this kind of a set. So say let's again, for all of these constructions, I need to fix a Hilbert space first. So I'm working more concretely. So you can take sum over X and sum over Z, and also sum over Z. And also, I think you should also break the inversion symmetry. So if I take these four operators, maybe not all of them are required, but okay, let's just keep all four operators. Then what you can show is that the commutant is just generated by the translation symmetry. So there is a family of Hamiltonians which are obtained by putting in arbitrary coefficients here in front of these things, and I just ask what is the set of operators that commute with this family. I get it's this translation. Okay, and if I get rid of things like this, I also get the inversion symmetry. So there is so it at least it seems to me that all of the symmetries that we talk about have this implicitly, that there is a family. And now you can also do this for Kramer-Swanier with the half translations, which is what Pranay was talking about yesterday. So you have this operator D, which satisfies some algebra, which is, I think, this T times 1 plus eta or something like this. Correct? Yeah. So and for this, you can, if I want D to be in the commutant, so to have a local algebra, so it turns out I also need to include this eta, which in this case was just the Z2 symmetry. And if I get rid of this eta, it turns out there is no local bond algebra. But if I have D and eta, I can define families of Hamiltonians of this form, which is just this, and then also a zj plus 1 plus xj plus 1, j plus 2. And there's probably something else which I need to, there's also inversion here, but I can get rid of the inversion in some way. So you see that these are all self-dual terms. So this on periodic boundary conditions would commute with this Kramer-Swanier duality. And this is also a self-dual term. So I needed to choose two of them to generate a family. Right? Otherwise, it's just a single Hamiltonian and I run into problems. Okay. Yeah, maybe, I mean, those should be, so again, by the double commutant theorem, this is the algebra of all symmetric operators. So anything that commutes with this you should be able to generate them just from these two. Yeah, so the logic is both ways. I'm just saying that for all of the C's that we study, like all of the symmetries that we study, there is a family of local Hamiltonians such that you can solve for the commutant and get this. So if I get rid of, say I want to get the family of Hamiltonians that only have D as the symmetry without the Z2 symmetry, it turns out that you necessarily have to make this non-local. So there is no local Hamiltonian that will realize only the Kramer-Swanier as a symmetry without having the Z2 symmetry. But then if I put in the Z2 symmetry here, there is a local family. And these are kind of the symmetries yeah. Yeah, so I think maybe with the ZX calculus, there might be some way, but we did this numerically. And so, yeah, so a lot of this, I mean, in some easy cases, you can do this analytically, but these kinds of things, I think we just do on a system of 6 sites or tensites and yeah. And then try to find local operators that commute with this, and then you go backwards. Oh, so there are methods to go from given any operator, and if I impose that this is local, there are some efficient methods, but I think I don't have time to, maybe we can discuss. There are these. Yeah. Yeah. No, all Hamiltonian. So that is the double commutant theorem. So everything that commutes with this set will be here. So all possible self-dual models can be generated from these two. Like that's my claim. I mean, I might be wrong about some technical details, but that's the idea. So if you take the commutator of these two, you will get another self-dual model. And then you can take a series of commutators to generate the set of all local models, which are self-dual. Right? Okay. Yeah, so it for these kinds of dualities, and it turns out that you really need to take the sums of these terms, and so it's not clear how to, at least to me, it's not clear how to reconcile it with this kind of a duality where you just sort of interchange E and M terms, but I think some of you can. Yeah. Mm-hmm. Yeah. So certainly, yeah. So yeah. So just as in like in an example which we discussed earlier, so where you have XX and YY, this family of Hamiltonians does not have a U1 symmetry, but if I fine tune them to have the same coefficients, I get U1 symmetry. So yeah, such things can happen, and really, like my way of thinking of it, which we can discuss maybe later, is given a Hamiltonian, you ask what is the local perturbation you can add such that your blocks are the smallest. And that's sort of the way, but we don't have a very practical way of doing this. Okay, so I think I'm almost out of time, but I really wanted to show more connections to things like hydrodynamics, but I can maybe sketch this and give you the reference. Yeah. I will do that. So again, this is sort of motivated by the question of how do you solve for the commutant. So given this bond algebra, we really want to Hj j plus 1 q equal to 0 for all j. And it turns out you can phrase this as a model, as a problem of solving for frustration-free ground states. So this can be written as, so if I convert this q into an operator, if I convert the operator to a state, you can write this as the Liouvillean annihilating this state, where the Liouvillean is really Hj j plus 1 tensor identity minus identity tensor Hj j plus 1. Okay. And so is this clear? So the way I go from operators to state is the standard Choi correspondence, or more simply, it is just you have an operator C mu nu. You just map this onto a state, which looks like C mu nu, mu nu. So there is this correspondence, but then you can go one step further and write a frustration-free Hamiltonian. So let me just write it as L dagger L, just to make clear that this is Hermitian. Right. So my claim is that this problem is completely equivalent to this problem where I just find a bunch of local Liouvilleans that annihilate this symmetry operators, which is completely equivalent to finding the frustration-free ground states of this operator here. So this super operator, which we called as super Hamiltonian. And this is work done with Leszek Motronik, 2023. Right? Okay. The reason these two are equivalent is just that this is a sum of positive semi-definite terms. And if I have a sum of positive semi-definite terms that give me 0, each of those terms should give you 0. And then you can go backwards, and then each of this should give you 0. And then this is equivalent to this. Right? So this is like a frustration-free ground state problem, which Haruki discussed in detail. And it's frustration-free because like each of these terms are annihilating this, and you can just find the ground state. There are, again, efficient numerical methods to do this, which is also in one of our papers, because this is a frustration-free problem. But let me just give you one example of how this works. So suppose I take xj plus 1 plus yj plus 1 and zj as my bond algebra. Now, the commutant of this is the U1 symmetry, but suppose I did not know that and I want to go through this route to solve things. So I construct the Liouvilleans from these terms. So Liouvilleans are just H tensor identity minus identity tensor H. So I can treat it as an operator on two copies of the Hilbert space. So the Liouvillean here, if you do this, so the Liouvilleans are basically like, so suppose I call this the top and bottom rung. So I have xx plus yy on the top tensor, or minus xx plus yy on the bottom with some indices. And then, so this is one of the Liouvilleans, and then there is also a Liouvillean corresponding to this term, which is just z on the top minus z on the bottom. Right? And you can construct this kind of a super Hamiltonian starting from this, and you find that what you get is something that looks like a, so on this two-leg ladder, you have rungs of this form. You get a super Hamiltonian that looks like you have products of xx plus yy. Right? When you square this, you get products of xx plus yy, and the squares of them. And so maybe I don't have time to go into the details, but what effectively happens, you can do this exercise more carefully. You can, if I define, say, composite spins, which are basically spins on each rung. So I just redefine the Hilbert space by just composing these two rungs, and then I define some composite spins. What you find is that the effective Hamiltonian that you get is like the Heisenberg model, the ferromagnetic Heisenberg model, on these effective spin degrees of freedom. So you get something like S tilde J, S tilde J plus 1. Again, these are vectors. And you will, so there are also other spin degrees of freedom, which turn out so to preserve the Hilbert space, I also need to define these kinds of composite spins, but then it turns out that these just don't enter the low energy physics. So because I'm interested in finding the ground states, I can just focus on the low energy sector, and it's sufficient to work in these two set of composite spins. And so you get the Heisenberg model. Okay, no, I think it's fine. So you get these Heisenberg models. So this is also a ferromagnetic Heisenberg model. The ground states of this ferromagnetic Heisenberg model are well known. So these are just this full SU2 multiplet. So you have this state, you have states that look like this. Where I flip one of these composite spins, and then I have states that look like various kinds of spins, various kinds of spin flips, right? So you have L+1 ground states, which are just composed of these spin flip degrees of freedom, right? And so these are the ground states of my super Hamiltonian, and you can try to go back to the operator language. So now all states in this two-leg ladder can be reinterpreted. I mean, you can go back to the original interpretation of operators. And then if you do this carefully, which I think I have or I have not, so if you do this carefully, you see that these L+1 ground states just map onto the identity operator, and then you get a sum of Zj operator, and then you get a sum of Zj, Zj1, Zj2. And then the whole set of states, the whole set of operators, which are basically all powers of your Zj operator. Okay. I think I just wrote them in the wrong basis. So let me just define this as composite spins in this direction, and then I define my new composite spins as this. If you do this, so this minus this. So if you do this, it turns out that this is just the identity operator on the site J. This is just the Z operator on site J. And then this tower just literally reduces to the identity, the sum over Z and sum over Z whole square and so on. So the L+1 ground states of the Heisenberg model are essentially the L+1 objects in the commutant of this. So the commutant of this was basically sum over Zj, and it's generated by sum over Zj, and I said that there are L+1 objects. And so you can sort of make this correspondence. And then you can also ask questions such as, so I constructed this super Hamiltonian. What are the excitations on top of this super Hamiltonian? So there is this super Hamiltonian P, which have these as the ground states. And then you can ask, what do these excitations of the super Hamiltonian mean? So once I have this, I can also start looking at excitations. And it turns out that those have a nice relation to hydrodynamic modes. Because you can construct like spin wave excitations on top of these, which have a k-square dispersion relation. And this dispersion relation is k-square precisely because of what Haruki was saying. So this is a frustration-free model. You can never get a k dispersion. So any gapless system which is frustration-free should at least have a k-square dispersion. And this sort of manifests nicely. And there is a connection to hydrodynamic modes, but I would need another lecture to go into that. So maybe I'll just close here with some references. So this is our paper, and on the hydrodynamic connections, there is also a paper by Ogunaike, I think Feldmayer, and Zhongyan Lee around the same time, like maybe a few months apart, where you can read this kind of a connection. So it turns out that you can deduce how the hydrodynamics of systems with continuous symmetries emerge by just studying this spectrum of the super Hamiltonian and relating them to 2-point correlation functions and so on. So with this, I can close. So thanks.
Questions?
Hydrodynamic modes are usually related to some symmetries. So these are realization of those symmetries.
Yeah. So whenever you have a U1 symmetric system, it turns out there are hydrodynamic modes, and a concrete way of seeing those hydrodynamic modes are excitations on top of the symmetries. So if here these were kind of the symmetry operators. But now you see, now you consider some operator that looks like e to the I k j, zj for small k. So if k is 0, this is an exact symmetry. If k is small, it turns out this gets some energy here. And there is a way to make concrete connections between this and random circuits, where you can actually do a precise computation of like 2-point correlation functions and hydrodynamic modes. I think we can discuss.
More questions? Okay, we will see. So let's thank Sanjay once more.